Hello, future engineers, subscribers, viewers, and students. Here is another video in plane and solid geometry, part 3, and this is also part 3. This is about applications of the theories, principles, and formulas discussed in plane and solid geometry 3. So let's start with problem 4. A truncated prism has a volume of 5.4 cubic meters. The base is a square and the altitudes through the corners of the base are 0.9 meter, 1.10 meters, 1.20 meters, and 1.25 meters. Determine the length of the edge of the base. So this is a truncated prism. The volume is area times the average height. Of course, the average height is sum of the heights divided by number of heights, which is 4. And the area is area of a square, which is base edge is square. So 5.4 equals e squared times the quantity 0.9 plus 1.1 plus 1.2 plus 1.25 over 4. So solving for e with your calculator there, so e is equal to 2.203 meters. Problem 5. A trough has ends that are isosceles trapezoids measuring 2.4 meters across the top, 1.8 meters across the bottom, and 1.2 meters high. The ends are 6 meters apart. If it is filled with oil weighing 8,000 newtons per cubic meter, determine the weight of oil in the trough if its depth is 1 meter. So weight is equal to specific weight. Let's express the specific weight in kilonewtons per cubic meter. So 8 kilonewtons per cubic meter times the volume of oil. While the volume of oil is area, which is trapezoidal section, times 6 meters. So let's have the details of the area. So we will call this part x so that the upper width of the oil surface d is equal to 1.8 plus 2x. And from the figure, so the area of the trapezoidal oil section would be 1/2 of b plus 1.8 times 1. So weight is equal to weight of oil equals specific weight of oil times volume of oil. So 8 gamma of oil times area of oil times 6, where the area of oil is, we need to solve for x by similar triangles. This is 0.3. 0.3 is 2.4 meters minus 1.8, so that's 0.6 divided by 2 because this is an isosceles trapezoid. There is also x on this side, so that's why there is also 0.3 equal to that. So that's why we have 0.3 meter. So x as to 1 equals 0.3 as to 1.2. So x is 0.25 meter. So b is 1.8 plus 2x. 1.8 plus 2 times 0.25. So the upper width of the oil surface would be equal to 2.3 meters. So substitute into this formula here. Weight of oil is 8, quantity 1/2 times quantity 2.3 plus 1.8 times 1 and times 6. Weight of oil therefore can be computed. It is equal to 98.40 kilonewtons. Problem 6. A cylindrical vessel has circular closed ends 1.2 meters apart containing water to a depth of 50 cm. The circular ends are 60 centimeters in diameter. When the vessel is positioned upright, determine the depth of water in the vessel in centimeter. So let's have the end section of the vessel, which is circular, and in the upright position the volume is just pi radius 30 squared times the depth. So it is the depth that is required. But in the horizontal position, this is the horizontal end. So the radius of the vessel is 30 cm, the depth is 50 cm. So that's why this is 50 minus 30, so 20. Then I'll call this angle theta over 2. The entire angle of this sector is theta. So that's theta over 2. Cosine theta over 2 equals 20 over 30. Volume is pi 30 squared times depth, and it is also equal to area of this water section below the 50-meter deep water section, and times perpendicular to the board, which is the length of the vessel, 1.2 meters, 120 centimeters, so 120 cm. So the depth in terms of the area is 0.04244 area of water surface. Then, to compute for the area of water surface, which consists of this big sector here and this triangle, we need to compute theta. Cosine theta over 2 is equal to 20 over 30. So theta equals 96.38 degrees, and in radians times pi over 180 degrees, that's 1.682 radians. So area of water surface is area of sector, which is 1/2 radius squared 30 squared times angle 2 pi minus 1.682 plus area of triangle 1/2 30 square sine of theta, which is 96.38 degrees. So with your calculator there, area of the water section is 2,517.746 square centimeters. Substitute into this formula. So D equals 0.04244 times 2,517.746. So the depth is in the upright position is 106.9 centimeters. So we have problem 7. A cylindrical tin can holding 2 gallons has its height equal to the diameter of its base. Another cylindrical tin can with the same capacity has its height equal to twice the diameter of its base. Find the ratio of the amount of tin required for making the 2 cans with covers. So 1 gallon is 231 cubic inches. So the total surface area is twice the area of the base, which is circular, plus lateral area, which is circumference times height. So the area of the base is 2 times pi over 4 diameter square. Then the lateral area is pi dh, where pi d is the circumference. Then the volume is area of the circle, pi over 4 diameter square times height. So for the first cylindrical tin can, the diameter, the height, the altitude is equal to the height or the diameter of the base. So let's begin with the volume. Volume is pi over 4 diameter 1 square times height diameter 1 also, because the height is equal to the diameter. So the diameter is cube root of 4v over pi, and expressing it in decimal, so diameter 1 is height 1 equals 1.08385 cube root of v. Then for the second cylindrical tin can, the height is twice the diameter of the base. So if the diameter of the base is diameter 2, so volume, same volume as the first, pi over 4 diameter 2 squared times quantity 2 times diameter 2. So diameter 2 is cube root of 2 over pi, 2v over pi. And in decimal, diameter 2 is 2 times, is height 2 over 2 equals 0.86025 cube root of v. So the total surface area of the first cylindrical tin can, substitute into this formula here, where h is equal to d. So area total 1 is 2 pi, quantity 1.08385 cube root of d square over 4 plus pi 1.08385 cube root of d square, because h equals the diameter for the first cylindrical tin can. So it is equal to 5.5358 volume to the 2/3. For the second cylindrical tin can, total surface area is 2 pi, quantity 1.86025 cube root of d square divided by 4 plus pi 0.86025 cube root of d. That's the diameter. This is the altitude, 2 times the diameter. Then in terms of d to the 2/3, total surface area of the second cylindrical tin can is 5.8122 v to the 2/3. Therefore, for the ratio, area of cylindrical tin can 1 over area, total surface area of cylindrical tin can 2. So that's the ratio. In decimal, that's 0.9524. So that's for problem 7. Problem 8, a pole in the form of a circular cylinder of altitude 18 feet and diameter of right section 0.4 of a foot has a base whose largest dimension is 0.5 of a foot. Find the lateral area of the pole. The lateral area of the pole is circumference of the right section times the lateral edge. So to help analyze the lateral edge, let's do the figure. This is the figure. So we have diameter of the right section 0.4, which is a circle, and the dimension of the base, largest dimension is 0.5 of a foot. So I'll call this theta. This is also equal to this angle here. And to solve for L, we have to obtain the ratio of opposite to hypotenuse. So the lateral area is perimeter of the right section times L, lateral edge, L in this case. And since the perimeter of the right section is circumference of a circle of diameter 0.4, so it is pi times 0.4 times L. So that's the working equation. To solve for L, we have here similar triangles opposite to hypotenuse. So 0.4 as to 0.5 equals, if this is theta, 18 as to L. So 0.4 as to 0.5 equals 18 as to L. So L is equal to 22.5 feet. Substitute into this working equation that is already set up. So lateral area is pi times 0.4 times 22.5. So the lateral area is equal to 9 pi square feet. Then next problem, find the volume and the total surface area of a pyramid having pentagonal base of side 6 cm and an altitude of 9 centimeters. The volume of a pyramid is 1/3 area of the pentagon times the altitude, which is 9. So this is the base of the pentagon. We'll just draw this. Then for the volume, 1/3 of the area of the regular pentagon times height over 3, while the total surface area is area of the pentagon, the base, plus 5 times, or in general n times, area of one face. The face is an isosceles triangle of base 6 and altitude big H, where big H is square root of apothene square plus height of the pyramid square. So the altitude is already 9. So we need to solve for R. So the angle here is equal to 360 degrees divided by 5, so 72 degrees. Then since this is only half of the central angle, so half of 72 is 36 degrees. So this is also half of 6 of 3. So by the way, the lateral area is 1/2 perimeter times big H. So area of pentagon plus 1/2 perimeter times big H. This is the base. That's the total surface area. This is the lateral area. Again, the lateral area is in general n times area of one face. Since the area of one face is edge 1/2 of base edge times big H, and big H is square root of apothem squared, small r squared, plus altitude of the pyramid squared. So if you want to imagine it, you just draw the pyramid so that you can analyze that big H is really square root of r squared plus altitude of the pyramid squared. And n times the base edge is perimeter. So that is why it is 1/2 of perimeter times big H. So tangent of 36 equals 3 over r. R is the apothem, so r is 4.129 cm. So substitute into this formula where area of pentagon is 5 times area of this isosceles triangle. The area is simply 1/2 of 6 times r. So volume equals quantity 5 times 1/2 of 6 times 4.129, then times 9 over 3. So volume equals 185.8 cubic centimeters. Then for the total surface area, so again H is square root of r squared plus 9 squared. So let's just proceed directly. Perimeter is 5 times 6. So area of pentagon is this. So total surface area is 5 times 1/2 of 6 times 4.129 plus 5 times 6 over 2 times square root of 4.129 squared plus 9 squared. So the total surface area is equal to 210.5 square centimeters. So problem 10. A pyramid is cut from a cube of edge 12 centimeters. The base of the pyramid is the face of the cube, and the vertex is the midpoint of the top edge of the face of the cube. Find the volume and the lateral surface of the pyramid so that we can visualize and set up the volume and total and the lateral area of the pyramid. So let's have the figure shown here. So this is the pyramid. So this is 6 because that's the midpoint. Half of 12 is 6. So for the volume, it is 1/3 area of the base, which is a square, times height, which is 12 also. So substitute, area is 12 square, height is 12. So 12 squared times 12 over 3. So the volume is equal to 576 cubic centimeters. For the lateral area, the area here, front and the rear is the same. So it is equal to 2 times area of the front face plus area of the left face, which is an isosceles trapezoid, plus area of the right face, which is also an isosceles trapezoid but of different dimensions. So total lateral area equals 2 times area of the front face plus area of the left face triangle plus area of the right face triangle. For the front face, it is just 1/2 of base 12, and this is the height because this is 90 degrees. This height here is square root of 6 square plus 12 square. So that's for the front face. For the left face, it is just 1/2 of 12. This is 12 and the height is also 12. Then for the right face, it is 1/2 of 12 times this height that is inclined. And this inclined height is simply square root of 12 square plus 12 square. 12, 12. So that's it. So area lateral is equal to 2 times quantity 1/2 of 12 times square root of 6 square plus 12 square plus 1/2 of 12 times 12, the area of the left face, then plus area of the right face 1/2 of 12 times square root of 12 square plus 12 square. So using your calculator, the lateral area is 334.8 square centimeters. Problem 11, determine the volume inside an elbow 15 centimeters in diameter and a radius of curvature of 12 centimeters. So we use the second proposition of Pappus, which is volume equals area of the circle, cross-sectional area of the elbow. So since this is an elbow, it is understood 90-degree rotation unless otherwise specified. So pi times by the proposition volume equals area times d distance traveled by the centroid, and the distance traveled by the centroid is radius of curvature times central angle, which is 90 degrees, and 90 degrees is pi over 2. So it is pi 7.5 square, area of the circle, times distance traveled by the centroid is radius of curvature 24, and angle is pi over 2, 90 degrees or pi over 2. So pi 7.5 square times quantity 24 times pi over 2. So the volume is equal to 6662 cubic centimeters. Then problem 12, a right circular cone is manufactured from a circular sheet of tin 120 centimeters in diameter. If 3 identical cones are made up from the circular sheet, what is the maximum volume of each cone? So since the cones are identical, so from the circular sheet of tin, we have to divide it into 3 equal parts. So the central angle of the sector, where it becomes the lateral area of the cone, is 360 degrees divided by 3. So that's 120 degrees or 2/3 pi. And the radius of the circular sheet becomes the lateral or the slant height of the cone, which is 60 cm as shown. So this is the angle of the sector, which this becomes the lateral area of the cone, and this arc here becomes the circumference, the base of the cone. So 2 pi r, equate it to circumference of the cone, base of the cone, and 120 degrees is 2/3 pi. This is the radius of the circular sheet, which becomes the lateral height of the cone, 60, half of 120. Then the volume of the cone is pi r square h over 3. Then to solve for r, we equate 2 pi r to radius 60 times central angle 2 pi over 3. So 60 times 2 pi over 3, r theta, remember, is equal to this arc length here, and we equate it to 2 pi r, which is the base of the circular cone. So 60 times 2/3 pi equals 2 pi r. So r is equal to 20 cm. So the altitude of the cone therefore is square root of 60 square minus r square. So substitute into the above formula. Volume is pi times 20 square times over 3 times square root of 60 square minus 20 square. So the volume of the cone is equal to 23695 cubic centimeters. Problem 13, each side of a cube is increased by 10%. By what percent is the volume of the cube increased? So when the cube grows or contracts, it remains a cube in shape. So we can apply the similar solids principles on similar solids here. So volume of the new volume as to the original volume is equal to the cube of the dimension over the cube of the original dimension. So if the original dimension is E, the new dimension would be 1.1 of E. So volume new over volume original equals quantity 1.1 of E cube over E cube. Cancel out E cube. So volume new is equal to 1.331 of the original volume. So that means the volume increases by this much, 0.331 of the original volume, and in percent, that's 33.1%. So percent increase in volume is equal to 33.10%. Problem 14, if the surface area of a sphere is increased by 30%, by what percent is the volume of the sphere increased? So we can still apply the principle on similar solids here. So ratio of volumes should be equal to ratio of surface area raised to 3 halves. So volume of the new volume as to original volume is the surface area is the new surface area is 1.3 of the original quantity to the 3 halves. So equals quantity 1.3 area original to the 3 halves over area original to the 3 halves. So cancel area original to the 3 halves and compute 1.3 to the 3 halves. So the new volume is 1.4822 of the original volume. So that means the volume will increase by 0.4822 of the original volume, and expressed in percent, that's 48.22%. So percent increase in volume is 48.22%. Problem 15. A conical tank is 9 feet deep and 6 feet across the top. Find the volume of water when the depth is 7 feet. So how deep is the water when the tank is inverted? So we can apply similar solids, the principle of similar solids here. So let's have the figure first. The radius of the top is 3 feet, half of 6. Then the depth of the cone is 9 feet. Then the depth of water in the cone is only 7 feet. So by similar solids, volume of water as to 7 cube equals volume of cone as to 9 cube. So volume of water as to volume of cone is 7 cube as to 9 cube. So volume of water is 7 over 9 quantity cube, and volume of cone is pi, radius 3 square, height 9 over 3. The volume of the cone therefore is 27 pi cubic feet. So this is 27 pi. Then the volume of water is equal to 39.91 cubic feet. Then in the inverted position, volume of air, by the way, is volume of cone with 7 pi minus volume of water. So volume of air is 44.913 cubic feet. In the inverted position, so that before we can solve for the depth of water in the inverted position of the conical tank, we need to solve for this height of air. So by similar solids again, volume of air 44.913 as to height of air cube equals volume of cone 27 pi as to height of cone 9 cube. So height of air is equal to 7.281 feet. Then the depth of water in the inverted position is equal to 9 feet minus 7.281, and that is equal to 1.719 feet. Problem 16. A right circular cylindrical vessel 12 centimeters in diameter and 15 centimeters high is tilted such that when the liquid is horizontal and cutting the diameter of the closed end, the liquid stops spilling. Determine the volume left in the vessel. So in this case, we use the Prismoidal formula. And before we can use that, let's have the figure so that we can analyze the situation. So this is the situation. This is area 1, one end, the other end is there, same, so pointed, so therefore the area is 0. Area 1, 0, area 2, 0. Distance between area 1 and area 2 is the diameter of the vessel, which is 12 cm. The height of the vessel is 15 cm, so the area of the midsection is this right triangle here, with dimension base 15 and height 6, the radius of the vessel. So Prismoidal formula, volume is L over 6, quantity area 1 plus 4 times area of midsection plus area 2, where L is the distance between end areas, so which is 12, area 1, area 2, 0, as already explained there, and area of midsection is 1/2 of 15 times 6. And that is 45 square centimeters. So the area, the volume can now be computed. Volume left is 12 over 6 times quantity 0 plus 4 times 45 plus 0. So volume left is 360 cubic centimeters. Problem 17, determine the volume of a regular dodecahedron if its total surface area is 2,973 square centimeters. So for the volume, it is 7.663 E cubed. And to solve for E, because the total surface area is known, and the total surface area is 20.646 E squared for a regular dodecahedron, then from here, we can solve for E. So 2,973 equals 20.646 E squared. So solving for E, E is 12 centimeters. Substitute into this formula. So volume equals 7.663 times 12 cubed. So volume is equal to 13,242 cubic centimeters. Problem 18, a cone 18 centimeters high is cut by planes parallel to the base at distances of 6 centimeters and 10 centimeters from the base. So for the first question, at what distance from the base must the plane be passed to divide the cone equally into two parts? Then B, what is the ratio of the volumes of the middle part to the largest part? So this pertains to the original situation where the cone is cut by planes parallel to the bases 6 cm and 10 cm from the base. Then what is the ratio of the surface areas of the middle part to the largest part? So let's have the original figure first. So these are the cutting planes, 6 cm from the base, and the other one 6 plus 4, 10 centimeters from the base. This is the middle part, this is the smallest part, and this is the largest part from the figure. So for number 1, let's have the figure. So this is the cutting plane, and the question is, at what distance from the base must the plane be passed to divide the cone equally into two parts? So by similar solids, we can apply similar solids principles on similar solids here. We solved for H1 first before H sub B. And since this cutting section divides the cone into two equal parts, so that means this is half of the volume of the entire cone, 0.5 of V, and the lower part is also 0.5 of V. So by principles on similar solids, 0.5 of V as to H1 cube equals V as to 18 cube. So 0.5 of V as to H1 cube equals V as to 18 cube. Cancel out V. solve for H1. So H1 is equal to 14.29 cm. Therefore, the cutting section such that the cone is divided into two equal parts, HB is 18 minus 14.29, and that is equal to 3.71 centimeters. For the second part, the ratio of the volume of the middle part to that of the largest part. So to apply the principle on similar solids, we combine the smallest part and this middle part here so that they constitute a cone to maintain the similar solid principle. So that is VSM, combined smallest and middle, as to height, which is 4 plus 8, so 12 cube equals smallest V sub S, because this is already a cone, as to 8 cube equals volume of the whole cone as to 18 cube, the height of the whole cone cube. So VSM is equal to 8 over 27V. V sub S is equal to 64 over 729V. So the middle part is equal to VSM minus the smallest part. So V sub M equals VSM 8 over 27V minus the smallest part 6 over 729V, and that is equal to 152 over 729 of V. Then the largest part is volume of the entire cone minus VSM. So V largest equals V minus 8 over 27V, and that is 19 over 27V. Obtaining now the ratio of Vm to V sub L, and that would be equal to 152 over 729V divided by 19 over 27V, and that reduces to 8 over 27. So it's 8 over 27. Then the other way, which is the shortcut, is it is 12 cube minus 8 cube to reduce this. Then for VL, it is 18 cube minus 12 cube. So V sub M over V sub L equals 12 cube minus 8 cube over 18 cube minus 12 cube. So it's like we subtract. So this is for V sub M, it is 12 cube minus 8 cube ratio. Then V sub L is 18 cube minus, we remove the cube of the height of this cone. So that's the shortcut. And we use this idea, because the result is the same, to part C, which is the ratio of the surface areas of the middle part to the largest part. So we just replace 3 by 2 because it is ratio of surface area, so these should be squares. So that is also 8 over 27. So 18.3, area of middle part to largest part is 12 square minus 8 square over 18 square minus 12 square. Instead of going through with this same idea here, the result would still be the same as this. So it is equal to 4 over 9. Then this is the final problem in this video. A regular tetrahedron has a lateral edge of 9 centimeters. Determine its volume and its total surface area. What is the volume of the largest sphere that can be inscribed in it? So for the volume, square root of 2 over 12 a cubed, that's derived in the lecture part. And it is equal to 85.91 cubic centimeters. The total surface area is 4 times area of equilateral triangle. Area of equilateral triangle is square root of 3 over 4 edge square. So times 4, so it is square root of 3 e squared, the total surface area. Square root of 3 times 9 squared. And that is equal to 140.3 square centimeters. For the volume for third pi r cubed, r is square root of 6 over 12 of the edge. So for third pi, square root of 6 over 12, 9 cubed. Quantity cube. So it is equal to 25.97 cubic centimeters. So that's it for this video.